In this video, we're going to look at differentiating exponentials and logarithms. So we're going to start off by differentiating y equals e to the x. Now, y equals e to the x has a special property in that it is its own derivative. So if y is equal to e to the x, then dy by dx is equal to e to the x. If there's a constant in front of x, then we just multiply that by what is in front, but the power is staying the same. So in this first example, we're being asked to differentiate 5e to the x. So if y is equal to 5e to the power of x, then dy by dx is just equal to 5e to the power of x. Again, it has that specific property. For this second one, we're being asked to differentiate 5e to the power 2x. Well, in that case, dy by dx is going to be equal to 2 times 5 gives us 10. So that's going to be 10e to the 2x. Remember, that power is staying the same. We're going to look at differentiating the natural logarithm function now. So the natural logarithm can be differentiated as follows. So if y is equal to ln x, then dy by dx is equal to 1 over x. And if y is equal to ln kx for some constant k, then dy by dx is also just 1 over x. And we're going to look at y in this second example here. So differentiating y equals ln 2x. So if y is equal to ln 2x, we need to remind ourselves of our laws of logarithms here. ln 2x, I've got ln of 2 being multiplied by x. That is the same as ln 2 plus ln x by our laws of logarithms. And the natural log of 2 is just a number, it's just a constant. Therefore, differentiating that is just going to give us 0. Therefore, dy by dx is just going to equal 1 over x, because I'm only differentiating this term. Differentiating that term just gives us 0. The last bit we're going to look at is differentiating exponential functions of the form y equals a to the x using the laws of logarithms. So if we look at this here, we've got y equals a to the power of x. Now in future, we're going to look at a way of doing this using something called implicit differentiation. But for now, we're just going to stick to our laws of logarithms. So if I've got a to the power of x, I can just write that as e to the ln a to the power of x. The e and the ln are cancelling out. The reason we're going to do this is it just leads us to, using some of the things we've done above, leads us to something that looks a little bit nicer to be able to differentiate. Now, if that's e to the ln a to the x, using our laws of logarithms, this ln of a to the x, I can write that as x ln a. So I've got e to the power of x ln a. So now if I try to differentiate that, dy by dx is equal to, well, I've got ln a being multiplied by x, so I can bring ln a to the front, and I've got lots of e to the x ln a, and then we can just use those laws of logarithms in reverse. So x ln a is the same as ln of a to the x, so that's ln a times e to the power of ln a to the x, and then e to the power of ln is just going to cancel out, and that's just going to leave me with a to the power of x. So that gives me ln a times a to the power of x, or in other words, a to the x lots of ln a. So if y is equal to a to the power of x, dy by dx is equal to a to the power of x ln a. If we had a constant in front of it, then we're just going to end up with a to the power kx, and then that constant k in front of ln a. So if we look at this example here, where we're being asked to differentiate 5 to the power of x with respect to a, then dy by dx is just going to be equal to 5 to the power of x ln 5, for the same reason as what we just looked at previously. For more GCSE and A-level maths content, subscribe to N Jackson Maths on YouTube.